So in this video, we'll get some review of properties of functions that we've talked about previously with a focus on quadratic functions. So first up, let's take a look at some graph behavior. And with this one, we're given a function. It is in vertex form. So with that, to start thinking about increasing versus decreasing, long run behavior, relative extrema, and intervals of concavity, actually, let's talk about doing that without a graph first, and then we'll graph it to double check. But let's say I'm just looking at this function. With this function here, what I could do is, with that negative out front, I know this is going to be concave down. So our parabola is going to look like this. I also know my coordinate, which is the vertex right there, is going to be at 2, 3. And with that, I can actually answer a lot of these questions. So starting with increasing, what I can see is my function is increasing to the left of the vertex. So we're going to be increasing all the way until we reach x equals 2. So I'm using is that x coordinate of my vertex there for when I switch from increasing to decreasing. So from negative infinity to 2, we are increasing. And then it switches to decreasing. So we'll do that from 2 to infinity. For relative extrema, we have a local maximum at the vertex. So that coordinate 2, 3 is a local maximum for relative extrema. And then for, I feel like I skipped over something, long run behavior. Let's actually do that last. Concavity. This parabola is all concave down, and that's going to be true for the parabolas. It's either going to be all concave up or all concave down. So if I wanted to describe where it's concave up, that's nowhere, but concave down would be all real numbers. So from negative infinity to positive infinity. Okay, last piece, long run behavior. I want to know where my function goes as we go to the right and to the left. So as we go to the right, so as x approaches positive infinity, our function's going downward. So that would mean f of x approaches negative infinity. So that would be as we go to the right, our function is going down off to negative infinity. And then as we go to the left, same thing, we're going down, so we'll be going to negative infinity there too. And with parabolas, it's going to match up each time. So as we go to the right, as we go to the left, our function's going to either both be approaching positive infinity or both be approaching negative infinity. So with that, all I needed from my function was whether we were concave up or concave down and where is the vertex located. And I could answer all those pieces. Now to get a more accurate graph, let's go ahead and graph this. So let's see, at positive 2, positive 3, we would have our vertex. It's opening downward. And then what I would notice is we're not doing any sort of vertical stretch or compression here. So that I could just kind of use those distances, 1, 1, 2, 4, to get a structure going. I could even go, let's see, 1, 2, 3, and that would be 3, 6, 9 down below. And then with symmetry over there. And with that, we get a pretty good graph going. Just a few coordinates. All right, there we go for that. Now let's take a look at composite, what we would need to do if we wanted to take the inverse of a quadratic, and average rate of change and difference quotient. So, composite function. We want to go f of g of x. So, outside function is f, and g of x we're inputting x minus 1 squared minus 3. So f of x tells us to take 3 times our input squared plus 2 times our input minus 1. Now you have an option here. You can keep g of x in this structure. If you wanted to, you could expand it out. and it might make things easier. That's kind of a toss-up. It's up to you. I'm going to go ahead and expand it out. I think it is going to make things simpler. I think we'll get to a point where we'll need to expand it anyway. So x minus 1 quantity squared should be an x squared minus 2x plus 1 when we FOIL that out, and then taking 3 away. So that's going to be the same as x squared minus 2x minus 2. I'm going to go ahead and plug that in here. And x squared minus 2x minus 2. Okay, it's going to be tricky here, and I'm going to write this out as all of that squared is the same as having x squared minus 2x minus 2 times x squared minus 2x minus 2. And then I'm going to go plus, and I'm going to go ahead and distribute that 2 in, so that'll be a 2x squared minus 4x minus 4 and minus 1. So the tricky part is multiplying this out, and it's just kind of not hard, it's just messy. So what we need to be sure that we do is distribute the x squared, distribute the 2x, and I'm going to run out of space here, but distribute that negative 2 as well. Here we go. 3 times x squared times x squared minus 2x, x squared minus times minus 2. All right, distributing the negative 2x would be a negative 2x cubed plus 4x squared plus 4x. All right, distributing the negative 2 minus 2x squared plus 4x plus 4. And then I can't forget, I'm going to close those parentheses, and then I have that plus 2x squared minus 4x. Minus 4 minus 1 is a minus 5. So everything in those parentheses is just that expanded out. It's messy, but we can do. It's our multiplication of polynomials. What I'm going to do is simplify what's inside those parentheses there. So next up, I'm going to go equals 3, and let's see what I got here. So I have an x to the 4th. I think that's going to be all alone. Let's see, x cubed. Okay, so let's go. We have an x to the 4th. We have a minus 4x cubed when we combine those together. Let's see, x squared. So let's see, minus 2 plus 4, so positive 2, minus 2. So that's all going to turn into a 0, so we won't have an x squared term. And then we have a 4x plus 4x plus 8x. And then a plus 4 as a constant there. And then outside of the parentheses, plus 2x squared minus 4x minus 5. Okay, distribute the 3. Keep everything on the end there. And then combine like terms. So we have a 3x to the 4th. We have a minus 12x cubed. Let's see, plus 2x squared. 24 minus 4, so plus 20x. And then a 12 minus 5 for a plus 7. And there is our composite function. We did it! Yay! Hope I didn't miss any steps. They're going too fast. As a good exercise, if you skipped over this piece, take a moment to try out this multiplication of two polynomials. It's very important to be able to expand something like that. It doesn't come up too often, but it is a skill that'll be good to have. Okay, are the functions f of x and g of x one-to-one? So if we think of a quick sketch here, this 3x squared plus 2x minus 1, that's going to be a concave up parabola. That is not one-to-one. And then my x minus 1 squared minus 3, that's also a concave up parabola, also not one-to-one. So those two functions are not one-to-one because we failed that horizontal line test. So what we can do is with g of x, and we could do this with f of x too, but we're just going to focus on g of x here. So at x minus 1 squared minus 3, what we could do is restrict the domain of g of x to find an inverse. So if I think of a quick sketch of this, this is a parabola that opens upwards and it has the vertex positive 1, negative 3. So we're down here and we have a parabola. And what I need is just half of this parabola. So what we're going to do is when I create the inverse, I want to have a square root function, something like this. So actually, even if my vertex is 1, negative 3, my vertex is going to move to negative 3, positive 1, right? Because the x's and y's switch. And then let's say I want to have it go this way. So what we could do is, let's see, if we have that coordinate there, that would be a 0. Sorry, doing quick mental math there. 0 minus 1 squared, 1 minus 3, negative 2. Oh yeah, that makes sense. 0, negative 2. So then we would have, so that would be the coordinate negative 2, 0. So that's on the other side. That would be down here. And I want to graph up above. So that tells me I'm actually going to focus on this side right here. Okay, so what I'm going to use for g of x is I'm going to fix the domain so that we're going from 1 on to infinity. So I'm going to start at 1, go up to positive infinity. And then what that means is when I take the inverse function, so here's just my sketch of the inverse function, that means then my range is going to go from 1 to infinity, right? Because the domain of our original function becomes the range of our next function. Okay, so I've restricted the domain, and now what we can do is taking that x minus 1 quantity squared minus 3 and say that equals to y. Let's go solving for what will eventually be our square root function. So let's switch x and y, add 3 to both sides, take the square root of both sides, but we don't need to do plus or minus here because we're only using half of it. So technically, we have a plus or minus here. We're only going to use the plus. So we have the square root of x plus 3 is equal to y minus 1. And let's go ahead and add 1 to both sides. Plus 1. And that would be our function on the restricted domain. There's our inverse function. If we restricted the domain of g of x, this works. Okay, so a little bit of work to think about that restricted domain and making sure we're getting the correct part of the graph. That all lines up. Okay, average rate of change. Let's go with f of x. So f of x is 3x squared plus 2x minus 1. And we're going to go from negative 3 to positive 2. So let's go f of 2 is going to be 3 times 2 squared plus 2 times 2 minus 1. So that's going to be a 12 plus 4 minus 1. So that's going to be a 15. F of negative 3 is going to be 3 times negative 3 squared plus 2 times negative 3 minus 1. So that'll be 27 minus 6 minus 1, which is 20. So if we're taking f of 2 minus f of negative 3 all over a 2 minus negative 3, f of 2 is 15. Subtract away f of negative 3, which is 20, all over 5, which will be a negative 5 over 5. So we're getting out negative 1 for our average rate of change. Okay, last piece here is a difference quotient, which actually in the power function video where we did a difference quotient, we also used a quadratic there is a quadratic that was in the power function form, so it's a little more straightforward. But let's see this again. So we're going to use that x minus 1 squared minus 3. And you know what? Let's go ahead and expand this out. Let's use the expanded form. So that'll be easier for simplifying, which we already did up here. So x squared minus 2x minus 2. So if we want g of x plus h, we're going to need to do x plus h quantity squared minus 2 times x plus h minus 2. So we're going to have an x squared plus 2xh plus h squared from that expanded squaring. Distribute the negative 2, and we still have a minus 2 at the end there. And nothing combines, so it would stay just like that. So for g of x plus h, let's plug in everything we just found there. So x squared plus 2xh plus h squared minus 2x minus 2h minus 2. And then here we're going to subtract g of x, which is this x squared minus 2x. And what I'm going to think about is that that negative out front needs to distribute into each of the terms. So where I have positive x squared, I'll actually have minus x squared. Where it's a minus 2x, it would become a plus 2x. Minus 2 would really be a plus 2. So all the signs switch in g of x. And then we go looking for things that cancel. So x squared minus 2x plus 2x minus 2 plus 2. So we're left with 2xh plus h squared minus 2h, and I have an h that'll factor out there. So we'll have h comes out, and we'll be left with 2x plus h minus 2 all over h. And we get to that point where the h's cancel, so we have 2x plus h minus 2 left. And we're done because we got that h in the denominator to cancel. So with this, if you're given vertex form, just know you can always switch to standard form because sometimes that'll be easier to work with. It was kind of nice to have vertex form when we did the inverse because we get to take that square root of both sides. Because we need to do some factoring in order to solve that. So that worked out nicely, but in other cases, it seemed that expanding it worked best for us.